quickly while we're waiting up. So I'm Anna Carlin, for those of you who haven't met me. This is Adit right here, who's one of the organizers, and the third organizer is Seb, who I've lost. He might be out in the hall, but you'll see him later at the next lecture. That's Seb walking. Okay, good morning, everyone. Welcome to the MSRI-sponsored Math and Machine Learning Summer School. It's a great pleasure to have you here, and I'd like to welcome our first speaker, Rob Schapire from Microsoft Research, who will be talking about statistical learning theory.
Okay, thanks. All right, so as Anna said, I'm Rob Schapire. I work at Microsoft in New York, and I've taught and I do teach at Princeton regularly as well. So what I'm going to be talking about is largely extreme compression of a part of a course that I teach at Princeton. So we'll find a way to put a link on the website to that course. So if you want to do more readings, and there are scribe notes also. I'll warn you, though, that the answers to some of the problems I'll be giving are in the notes for that class. So if you come across those, just avert your eyes or something. Let's see. I just want to make a small request. If people will forgive me, I would like to ask that people not use cell phones and laptops and other devices. I understand if you want to take notes, that's fine. You might want to turn off the Wi-Fi and the connectivity if you're doing that. Goes for streaming at home, too. No left? Oh, okay, that doesn't work. Okay, so I'm talking about supervised learning or statistical learning. Somehow the course got listed under two different names. So I guess statistical supervised learning, the foundations. And since I'm the first one, maybe I should talk a little bit about machine learning, what machine learning is. So machine learning studies automatic methods for learning to do stuff, learning to complete a task, or learning to make predictions, learning to make intelligent decisions of some kind. And it's based on observations, examples, data, experiments, being taught. In other words, it's about learning to try to do better in the future based on experience in the past. And the emphasis is on automatic methods. We're looking for methods that are fully automatic, off the shelf. You can just download it off the web and it'll work. At least that's the hope. The hope is for methods that don't require a human in the loop. Machine learning is a core sub-area of artificial intelligence because, well, if you want to develop an intelligence, we feel that learning is going to be necessary for that. And on the other hand, for something to be considered intelligent, we would expect it to need to be capable of learning as well. Machine learning has also become a core area of data science, since it's about how to get something out of data. So the goals of machine learning are to develop algorithms, general purpose algorithms that will be of practical value. So we're looking for algorithms that are efficient and that are easy to use, general purpose, off the shelf, cheap, flexible, and that will give results that are very accurate. And in some cases, we also want to get interpretable results. We want to learn something about our data. That's often a secondary goal. Often it's more about developing something that's accurate. So you can think of machine learning also as developing methods for programming by example. So if you're just trying to create a program, why do it by example? Why not just write the program directly? Well, a lot of times using machine learning, we can get results that are more accurate than what you could get by writing a program directly. And the reason is that with machine learning actually looks at the data. It's based on statistics. Actually looking at the data is one reason. And also machine learning algorithms can look at very large volumes of data, much more so than humans. Another reason why we might want to do that is because humans often have knowledge that they don't know how to access directly. So for instance, in recognizing a handwritten character, so you want to recognize a handwritten character by the letter of the alphabet that it represents. So we all know how to do that if you know how to read. And, but on the other hand, it would be extremely difficult, if not impossible, to directly program a computer to do it. So you have knowledge, but you don't know how to access that knowledge. So this gives us a way if we can just label a lot of examples and have the computer learn how to do it. I would argue that studying machine learning is also worthwhile because it can help us to understand the phenomenon of learning itself, not just machine learning, but learning in general. I kind of don't like the name machine learning because of the emphasis on machines. I actually think it's a broader field than that. I think it's about learning in general. So learning by any kind of system, learning by animals, learning by people, learning even other systems like adaptive systems like evolution, trying to understand them as well. So machine learning might be able to help us to understand, I think it does help us to understand questions like the dilemma between nature and nurture. In other words, how much has to be built in and how much is learned, which is a very fundamental question in areas like linguistics, psychology, and so on. Also, I think it can help us understand philosophical questions like what is simplicity and why is simplicity helpful in the context of Occam's razor, which we'll be talking about. So here we're talking about theoretical machine learning. So the goals of theoretical machine learning are much the same. We're trying to design and analyze efficient learning algorithms. We're trying to develop insights and intuitions that will help us to develop algorithms that are of practical value, to design them and understand them. We want to be able to understand things like what makes a learning problem hard or easy. What is the intrinsic difficulty of a learning problem? And we want to be able to try to explain things that are seen in practice. So one of the great things about machine learning is this interaction between theory and practice, the more empirical side and the more theoretical side. I think that's what's largely driving the success of machine learning. Some people might disagree with that, but that's what I believe. So with that as introduction, in this part of the course, we're going to be focusing on one very simple learning problem. We're taking a mathematical approach, so that means starting with the simplest problem and working our way up, and that's what we're going to be doing. So we're going to be focusing on a very simple learning problem, which is the problem of learning by example. Okay, given a set of examples, you want a learning algorithm to come up with a rule for being able to classify those objects. So a very standard example is something, the one I already mentioned, where you want to classify images of letters by the letter of the alphabet that they represent. So you want to be able to give a learning algorithm a handwritten character, like here's an image of a handwritten letter A together with its label, which is that it represents the letter A. And we want to give the learning algorithm a set of examples of this kind, of these handwritten characters, together with their labels. And we want to feed those to a learning algorithm. And the output of that learning algorithm should be a prediction rule, which takes as input a new example, which can take as input a new example, say a handwritten image like this one, and accurately output as the correct letter of the alphabet. Okay, it's a very simple problem. Everybody okay so far? Okay, so let's see if we can, so let's try this out. Okay, I'm going to ask you, well, first I'm going to ask this to work. Oh, sorry. Okay. So I'm going to ask you, everybody see that okay? To be this learning algorithm over here. So here I've got a bunch of examples. So here the examples are integers. Okay, and they've each been labeled. Here the classes are just positive or negative, plus or minus. And the goal is to come up with a rule that will let you predict what the labels would be on new data, and say on these test examples at the bottom. Everybody understand what I'm asking you to do? Anybody? Well, maybe think about the examples in sorted order. Well, the next one's even harder. Okay. Okay, yeah?
Plus, minus,
Can you want to flesh that out? Oh, the prediction is plus, minus, plus. Oh, I see.
minus, minus. The prediction is plus, minus, minus given the
Oh, okay. So how did you get that?
Well, the data seems to be like with a central section which has pluses and the extreme set of minuses, and like the first two are kind of simple because they're within range, and the last one is closer to the minus boundary than it is to the plus boundary, so it's minus.
Okay, good. Good. So yeah, if you'll notice that kind of in the middle range, the examples are positive, otherwise they're negative. So like if it's at least 67 and at most 173, it's a positive example. And if it's less than that, negative, more than that, negative also. Okay, so definitely 111 is in that range. 23 is definitely in the negative range. But 55 falls between 46, which is negative, and 67, which is positive. So you said it was negative, but it's kind of a crapshoot, right? It's not really clear what
It's closer to the 46 than it is to the 67. So.
Okay. Okay, good. Okay, everybody understand the rule? Okay. So let's try a different one. Maybe it'll help if maybe I can make this bigger. Okay, maybe that's a little better. Wait, is this the same one? No. Okay, let me give you a hint on this one too. Convert the numbers to binary. Oh, okay, I did it for you. Okay. Yeah? Okay, let's see. The sixth digit from the left, right? So So this one? So you're focusing on this one, right? Yeah?
The lowest order bits are 1, 0, 1, and that's a positive.
The lowest order.
Sorry, there's the last one.
Almost. Almost.
Third and seventh bits equal 1.
The third bit?
Sorry, third from the right.
Oh,
and
okay.
seventh from the
Third.
right.
Computer scientist, yeah, third. And this one, seventh. Okay, good. If they're both 1, then it's positive. Otherwise, they're negative. Okay? Good. Okay, so what was the point of that? What do we get from that? Okay, we're done with that. So the first point I wanted to bring out with that is that more data is better. Okay, so on the first one, we could do a pretty good job of classifying points in the middle range and points that were well to the left of it or well to the right of it. But then we had that in-between number, that 55, which kind of fell in between, and we didn't really know where to draw the boundary. We kind of drew it arbitrarily. And maybe with more data, we would have been able to refine that boundary between plus and minus better. Okay, so that's one thing, that more data is better. Another thing is I didn't tell you you had to come up with a consistent rule, a rule that would agree with all of the examples I had there, but somehow that seemed natural and implied that if you look at data, you want to come up with a rule which is consistent. I mean, you could have come up with a rule that said everything is positive, right? It hadn't been done, but somehow it feels natural to come up with a rule which is consistent. Ooh. Yeah?
So you could have put up an example in which you just randomly assigned pluses and minuses to numbers and asked us to figure out the rule.
Yep.
More data really help us then.
Not clear. Yeah, not clear. Hold on to that idea of giving examples random labels. We're going to come back to that. Okay? Okay, so that's the second point, that it was natural to come up with a rule which is consistent. And the third point is that I would argue that you were looking for a rule which is simple. So when you had a hard time with the first example, you could have suggested something like, I don't remember what the numbers were now, but you could have suggested, it's a positive example if it's 67 or 138 or 156 or 173. Just listed the positives, otherwise it's negative. That would have been consistent, but it doesn't meet that criterion of simplicity. Somehow we're looking for something simple. And in the second example, where it really was a hard problem to try to figure out what the pattern was there, because you were looking for rules of a certain kind, I'm guessing, what was inside your brains, but I'm guessing that you were looking for rules or patterns of a certain kind based on maybe the ordering of the numbers. And once I suggested to convert to binary, then that changed your point of view and it changed your notion of what a simple rule is. So you started thinking about different rules. So it's natural also to find a simple rule. And that notion of simplicity is tied up with expectations. So it has a lot to do with what we expect to see in the data. We expect a rule, to find a rule which is simple. And on the other hand, we consider a rule simple if it matches our expectations. So this notion of simplicity and prior expectations are all tied together. So what we've done, or what I'm trying to bring across, are the three conditions that are enough for learning, that are sufficient for learning. The three conditions that we need are enough data, and the second one is we want to have good fit to the training data. Okay, which means that we either want to have a consistent rule with consistent or at least few mistakes. on the training data. Just a little bit of warning on the word consistent. I'm going to use the word consistent a lot. All I mean by it is that it agrees with the training data. No mistakes on the training data. Has nothing to do with the notion of consistency from statistics. So if you've seen that, don't think about it. And then the third condition was that we want a rule that's as simple as possible. I think it was Einstein who said as simple as possible and no simpler. I think that's what we're looking for. So for that first criterion, more data is always better. More is more when it comes to data. But with these second two, getting good fit to the training data and coming up with a rule which is as simple as possible, there's a trade-off. There's a trade-off. So sometimes it's the case that we can get better fit to the training data by using a more complicated rule. Or conversely, we can come up with a rule which is simpler if we're willing to accept more mistakes on the training data. So there's a trade-off between these two. And balancing or understanding that trade-off is really at the core of what designing machine learning algorithms is about. That's really at the core of what it's about, trying to understand machine learning and designing algorithms. Okay, so in this mini course, what I'm aiming for is to really try to bring across an understanding of this, but at a theoretical level, not this hand-wavy level, but at an actual theoretical mathematical level. So most of what I'm going to be talking about is trying to understand these really fundamental questions. The most basic one is how much data, or the most basic ones are how much data is needed for learning, or equivalently, given a certain amount of data, what kind of accuracy or performance can we expect or guarantee? And also, how do we measure this notion of complexity and simplicity? How do we define simplicity? What is simplicity? And why does it have an effect on learning? And we also especially want to understand this trade-off. What is the trade-off between simplicity and complexity on the one hand and fit to data on the other? So I'm going to mostly focus on these foundational kind of questions. And then my hope is to talk about one particular practical algorithm. It's a practical algorithm, but to try to understand it theoretically, focusing on theoretical understanding. And if there's time, we'll look briefly at some generalizations. But I don't know. As I was going through my notes, I was more and more pessimistic about getting to that. So we'll see how it goes. Questions so far? Okay, good. So the first step then is to define the learning problem mathematically. That's the first thing to study mathematically. So for that, to study the learning problem, we need to come up with what's called a learning model. A learning model, a formal definition of what the learning problem is. And as with other models or other times when you want to study things mathematically, we want it to be rich enough so that it's capturing realistic aspects of the problem. But on the other hand, we want it to be simple enough that we're able to study it mathematically. And we'll start with the simplest cases and try to work our way up to stuff that's more realistic. So the learning model should answer certain basic questions. So what is it that's being learned? And where is the data coming from? In other words, how is the data generated? And how is it presented to the learner? And then what is the goal of learning? What is our criterion for success? What does it mean for the learning algorithm to succeed? So our focus, as I said, is on classifying objects, learning to classify objects in this way. So this kind of optical character recognition is one example. Another example is learning to classify email messages as to whether they're spam or not spam. And another example is learning to classify images as to whether they contain a face or not. Okay, so there are a few examples of classification problems, but there are many, many problems out there. I feel like when I would teach this class, I used to do a long list of examples to try to convince people how practical it is. I don't feel like I need to do that anymore. It's just like in the news all the time. So we're going to present our first learning model, really the main one we're going to focus on. So the first element of the model are these objects that are getting classified. So that's called an instance, or it's sometimes called an example, but the term example is a little bit ambiguous because example sometimes means just the object being classified, and sometimes it means both the object and its label. So example is a little bit less formal of a term. And usually, I'll be using the letter X, some variant on X for the examples. These instances come from some space called the instance space, or it's also called a domain. For that, I'll be using capital X. Okay, so little x is an element of big X. Big X is just the space of all of them. So for instance, little x might be an image, and big X would be the space of all possible images. Usually these instances are described by features. They're sometimes called features, attributes, dimensions. Like an image might be described by the pixel intensities of the image. For the most part, we're just going to gloss over that. It's not going to be much of a concern to us. Now, every one of these instances, like this one, has a label or a class. A label or a class. I think the fact that there's so many repeat terms in this field has to do with the fact that it's come from different directions, statistics, theoretical computer science, AI. So you end up with multiple terms for the same things. To keep things really simple, we're just going to assume that there are two possible labels, which are either usually 0, 1, but sometimes I'll often refer to them as plus minus, so a positive example, negative example, all means the same thing. And to keep things simple, we're going to assume that there exists a function that maps instances to these labels. Okay, so there's some true function out there that will take an image like this and map it to its correct class. It's an assumption. It's a moderately strong assumption. Later, we're going to relax it. So there's some function, C, which represents the truth. And it just maps instances from the domain to the labels, which are 0 or 1. And that labeling function, for our purposes, is called a concept. Okay, it sometimes has other names in other fields. We're going to call it a concept. Okay? So what that means is that each instance X is labeled by C of X. And our goal is to learn this concept C, or an approximation of it. Okay, more specifically, the goal is to output a prediction rule that will accurately predict or classify new examples. So the term I'm going to use for this prediction rule is a hypothesis. Again, it has different names in different fields. The name hypothesis is not great. Again, hypothesis is used in statistics to mean something completely different, so don't get it mixed up with that. Okay, so the hypothesis is also, it's really the same as a concept. It's really just a function that will take a new instance and predict its label. All right, so the picture is, let me take this picture over here. Maybe I'll just modify this picture. Oh, the first test of erasing. Well, not too bad. Okay. Right, so again, we're trying to design a learning algorithm. I usually use the letter A for the algorithm. Okay, the input to the algorithm are these labeled examples. Okay, so the first example is, say, x1, and it has a label c of x1 given by the concept. And I like to use m because I'm old-fashioned for the number of examples that are given to the learning algorithm. So there are m labeled examples that get fed to the algorithm A. And what it outputs is this hypothesis h. And what h does is it takes a new example. Of course, you know, it's a rule, so it can take any number of them. But we think of it taking a new test example, x, and outputting a prediction, h of x. Okay? Everybody okay? Okay. Now, generally, we assume that we know, or at least for now, we're going to assume that we know something about this concept. So if we know something about this concept, the truth, that's the same as assuming that we know it comes from some class of functions. So that class of functions is called the concept class. I use script capital C for that. Okay, so in other words, we're assuming, well, I already said the xi's are from the space X. And we're assuming that C, the true concept or the target concept, is coming from this class. So typically we know this class ahead of time. We know something about the concept we're learning, and we're trying to figure out exactly which one it is. Okay, and again, we're going to drop that later. But for now, we're assuming it. Okay. So now where do these examples come from? Where do these instances come from? Well, we don't really know where they're coming from. We feel like they're just the world is presenting them to us. So there's some, you know, when we go out to the world and we look for a handwritten character, we find one. And that's our example. So we can model that as the instances being generated at random, being generated at random. And to make things simple, we're going to assume that they're generated independently and always from the same distribution. So then there's the question of which distribution is generating the examples. So, you know, we want to make as few assumptions as possible. So you might, you know, want to make assumptions about handwritten characters coming from a normal distribution, or try to figure out something about the distribution. But it's certainly a lot nicer if we don't have to assume anything about the distribution which is generating these instances. So that's what we're going to do. We're going to study a form of learning that's sometimes called distribution-free learning, which means that we don't assume anything about that distribution. But we do assume that there is a distribution, let me call it D, which is generating the distribution, the instances. Sometimes it's called a target distribution. And again, we won't assume anything about it, except that it exists. So each one of the training examples is chosen at random from that distribution and independently, always from the same distribution. So they're independent and identically distributed, or IID. And importantly, we assume that the test examples also come from that same distribution. Okay, otherwise learning would be very hard. Actually, people study that, but it's a much harder problem. Yeah?
What is it about knowing which concept class our concept is being drawn from that makes that an okay hypothesis to work with and not knowledge of the distribution underlying the samples?
Yeah, fair enough. Not much, yeah. And we are gonna drop that later. Yeah. But yeah.
The target distribution.
I mean, are you asking why is it helpful or why is it reasonable?
I guess my question was, it seemed like it would be reasonable to make some sort of assumption of the target distribution as well, but apparently not.
I see.
So
I see.
why is that the line?
Oh, I see. I think it's just yeah. Well, you certainly could go that route. I think statistics tends to go that route much more, where they actually model the distribution, and parts of machine learning do that. But as we'll see, for the kind of learning we're doing, you really don't need it. All you need is that for the test and the training examples. You know, I mean, the goal is always to have as few assumptions as possible. So this is what we can do. Well, we can do more than this, but this is a good starting point.
From the initial data to the target, then it has a distribution because you put a distribution on X.
It has a distribution, but we're just not assuming anything about it. We're not assuming it's like comes from a class or something. We're just not assuming it's normal, for instance.
So do you also have like C's coming from a distribution? So let's say the first sample is coming from one C, the third sample is coming from another C. So are we assuming that?
We're not going to do that. That's more of a Bayesian type approach. So we're just assuming that, you know, the world decides on one of these concepts, and we're going to try to learn it. And so we're not assuming that it's coming from a distribution. Mm-hmm. Yeah.
What does the target in the target distribution stand for? So D equals target distribution?
Oh, why is it called a target? Well, I guess because it's the true distribution. I should have been calling. I mean, the true concept also often is called the particular concept which is generating the data is also called a target concept. I probably should have been. Okay, so concept really means any function that maps instances to labels, and then target concept is the truth. Yeah, I just needed to give it a name. So.
Thanks for the clarification. I think I heard the word target being used in a different way in one of the other questions that was being asked.
Oh, I see.
Somebody tried to map the instance to a target, which I don't think.
Oh, I see. No, I did not mean it that way. I just mean it's just often used to mean the true one. Yeah. Okay, good questions. Okay, so we need to measure how good this hypothesis is. We need to specify what the goal of learning is. So the way that we measure the good, or what we want is for this hypothesis to give accurate predictions. What we want is for this prediction, h of x, to agree with the true label, which is c of x. Or what we don't want is for there to be a mistake for h of x to disagree with the true label c of x, for the prediction to differ from the truth. That's what we don't want. That's a mistake. And to measure how good a hypothesis is, we just measure the probability of choosing a test instance which is misclassified. So the probability of choosing a test instance, x, from this distribution D, where it's misclassified. And this is called the error. Okay, the error of h, if we want to be explicit, with respect to the distribution D. This is called the error, or to be more specific, you might call it the generalization error. And that's what we measure, how we measure the goodness, or really the badness, of the hypothesis H. And so what we want is for this error to be small. We want this error to be small. So what we want, so later I'm going to fill this in. We want the error of h, we want it to be smaller than some small number epsilon. So in other words, we want it to be approximately correct, the hypothesis h to be approximately correct. But there's a little bit of a problem because these examples are being generated at random. And since they're being generated at random, there's always a probability, however small, that we'll get a really terrible training set just by bad luck. So for instance, if you're learning handwritten characters and you choose a whole bunch of examples, it's very unlikely, but it's possible that all the examples you got were vowels, say, right? That they were all vowels. So in that case, your learning algorithm might learn to recognize vowels, but it didn't see any consonants in training, so you wouldn't expect it to do well. Okay, but that's a low probability event. So we allow the learning algorithm to fail in this criterion, but we need to control the probability of its failing. So what we ask is that if we look at the probability of it realizing this success criterion, that probability should be close to 1, should be at least, say, 1 minus delta, where we're thinking of delta again as a small number. So this probability, always helpful to know what the probabilities are over, this probability is over the choice of the training sample. Okay? So this says we want the hypothesis to be approximately correct. And this says we want that to happen with high probability. So we want the algorithm to be probably approximately correct. And so this kind of learning is called PAC learning, which stands for probably approximately correct. So let me pull it together. So, okay, so we're going to say that class C is PAC learnable. And I'm going to say something else here in a second. If for every concept in this class C, oh, sorry. All right, I'm going to have to break down and get the eraser. Sorry, if there exists an algorithm A, so that for every concept in this class, and for any distribution or target distribution D, which generates the data, and for every epsilon bigger than 0, and for every delta bigger than 0, where epsilon and delta are appearing down here in this criterion. So A takes M random examples where each example is from D. And outputs a hypothesis H so that this criterion is met. Okay? So it's just pulling together all the other stuff I said. Now there's, yes?
I feel like I've kind of asked this already, but I'm going to ask it again. So underlying all this is that concept. Is that a deterministic function?
Yes. For now, we're assuming it's deterministic. Later, we'll relax it.
General,
correct.
Real life.
Correct. Okay. We're going to relax it. Okay, there's one more point, which is that sometimes it is helpful to allow these hypotheses to come from a different class than C. Okay, so we're also going to suppose that there's a hypothesis class or hypothesis space that I'll use big H for. And then the learning algorithm outputs this hypothesis from that space. Okay? And then just to modify this, we say that C is pack learnable by this hypothesis space if all the same things, and this is an H. And now I think the last point, I keep saying the last point, but I think this really is the last point, which is that how big should this sample size be, this sample size MB? Well, as you make epsilon smaller, we ask for this hypothesis to be more and more accurate. So as epsilon gets smaller, it's only reasonable that the learning algorithm should be allowed more data. So we allow M to be polynomial in 1 over epsilon, so that as epsilon gets smaller, you allow more data. And similarly with delta. And there's often other stuff, but let's leave that off. Yeah, for it to satisfy this definition. Okay. Okay, yeah.
What is the probability measure over the training sample? Do you assume that is to be uniform since you have random?
No, the training sample is coming from the distribution D. Okay, so the training examples and the test example are coming from the same distribution. Yep.
Are there metrics to measure the difference of two functions? And the reason why what you say to be like this entropy or Carroll divergence, is it just to be more realistic, or is there any other good mathematical properties of this metric?
Choosing a different metric besides these for measuring difference. Well, for different kinds of learning problems, a different kind of loss or way of measuring difference between functions might be more natural. I think for this learning problem, where we just want to classify things accurately as much as possible, I think this is the most natural criterion where you just measure the probability of making a mistake. But in other settings, you might want to do something different. Yeah.
And can you tell me this, the polynomial, can you say that there actually exists that relationship, the polynomial relationship in 1 over epsilon? Or is that just something we're assuming?
Okay, so for a class to be pack learnable, it needs to satisfy this definition. And so if it satisfies this, yeah, without, okay.
Oh, I see. The fact that it's pack learnable makes it polynomial.
Yes.
Or enforces the fact that it must be polynomial. Okay, thank you.
I don't think I have a good intuition for why M would have to scale with a polynomial versus like linearly or any other way with that error term. Can you maybe give me some intuition?
Oh, well, we're going to talk about what actually goes in here, right? So the game now that we have this definition, the game we can play now is to try to figure out exactly how much data is needed to satisfy this criterion. And so we're going to start talking about actual bounds. Okay? Yeah.
Sorry, one more thing. Is pack learnable like a really hard criterion, or is it an easy criterion?
I view it as the simplest case, but well, okay.
Gotcha.
We'll get to that to a degree. Yeah.
The probability measures that you're using. So when you define the error under
Yeah.
a distribution, we've assumed a distribution exists, right?
Correct.
And you're taking the probability under that distribution. So given H and C, that's a number,
Right.
right? And now you're asking, what is the probability a number is less than a number?
Okay, the probability
Yes.
over the training sample, so you get data, you run this algorithm, and it outputs a hypothesis.
So is that
So the hypothesis is a random variable, because it depends on the data.
Okay. So,
So the probability is over the training sample,
okay.
and where the random variable is H.
Okay. So that makes.
There's a conditional expectation.
Okay. All right. Now I got it.
Okay, good. Okay, so this is a definition. Yeah, one more.
You might have already answered this. I'm still having trouble. Like, m is a polynomial like, is that a number of random? Like,
Okay, it means that we're going to try to get a bound. Let me do an example, okay? I think it'll make it more concrete. Yeah.
So the error is over the test sample.
Yes.
And then the outside probability is over the training sample. And we're assuming that those are independent of one another, but they have the same distribution. Are we assuming anything about the size of the test sample? Do we need to?
We don't need to, because this is just a probability. It doesn't matter if this is the actual probability. If you were to estimate it, then it would matter with the test example. But okay, let me do an example, which I think will make things more concrete, hopefully. So it's not really obvious that this kind of learning should be possible at all when you think about it, because the domain, this domain is typically gigantic, even infinite, and we're trying to go from just this small polynomial-sized sample to some kind of rule which is going to be correct on almost all of the examples. So just from this little tiny sample, compared to the size of the domain, we want to end up with a rule which is correct on almost all the points. So let's look at an example. So this is probably the simplest example you could think of. So in this example, the domain is the set of real numbers. Okay, so the instances are just points on the real line. And our the concepts we'll be working with are just these simple threshold functions. Okay, so every concept is defined by a threshold, like this one. And if an instance, say out here, then that instance would be labeled positive because it's above the threshold. And if the instance is way over here, it's below the threshold, so it would be labeled negative. So this learning algorithm is faced with a bunch of random examples. This isn't going to look like a very random sample, but suppose that it is. Okay, these are all labeled positive. These are all labeled negative. Okay, so we know there's a threshold function which is consistent with these examples, but we don't know which particular function that is. Okay, so these kinds of concepts, I'm just going to call them positive half-lines. A lot of times you identify a concept with the set of points that are positive. So that would be this half-line, and it's positive just because I'm supposing it always goes to the right, that it can't go to the left. So that's our concept class. And given data of this kind, without knowing C, there are natural algorithms. Basically, we just need to choose a threshold anywhere in this region between positive and negative and call that our hypothesis. Now, just to make things really simple, maybe this isn't the smartest algorithm, but it's an algorithm. One algorithm we could use is to pick the leftmost positive point, which would be this one, and call it B, and then define our hypothesis to be defined by that threshold B. Okay, so B is the leftmost positive point, and then we'll just define our hypothesis, H, to be 1 or positive if this test point X is at least that threshold, and 0 otherwise. There's a very simple learning algorithm. Okay? So in this case, the hypothesis space is exactly the same as the concept space. Okay, so is everybody okay? So what is the probability of making a mistake? What is the error in this very, very simple case? Well, the probability of making an error is, well, first of all, if we get a new test example out here, then C says it's positive, and H also says it's positive. And likewise out here, both say it's negative. The only places where this hypothesis makes a mistake is in this region between the two thresholds. Okay, that will be the error region. So that's the probability of a test point falling in that region is exactly that error, that generalization error. Okay? So to show that this algorithm is PAC, that it satisfies these criteria, we need to bound the probability that this region will be bigger than epsilon. We want to bound the probability that that region will be bigger than epsilon. Okay, so so let's see how you could argue that. Oh my goodness. Whew. I didn't need to go to the gym today, that's for sure. Sprays for wimps. Oh yeah, that is easier. Okay. Yeah, if this teaching thing doesn't work out, I can be a window washer. Okay. Okay, so just to make things really, really simple, we will do things more generally. Just to make things simple, let's suppose that the distribution is uniform on the range 0, 1. So I'm just redrawing that picture. Okay, so here's 0, and here's 1, very blown up, just to make it, just to motivate, just to get our intuition going. Let's assume that that distribution is uniform. And again, the true, I think black works better. The true concept is somewhere in here. And what we can do is we can move epsilon to the right of that threshold C. So I'm kind of identifying a concept also with the threshold that defines it. And now I'm moving epsilon to the right of that threshold point. And let me call this region capital R. Now, if you think about it, how could this algorithm I described over here output a hypothesis whose error is bigger than epsilon? Well, if even one of the training examples falls in this region R, if any xi falls in this region R, then the hypothesis H will have to be either at xi or to the left. Then we'll have to have H falling in this region over here, which means that the region in between these cannot be bigger than epsilon because we define R to have size and probability exactly epsilon. Okay? So what that means is that the probability over the training sample that the error of this hypothesis that we generate is bigger than epsilon, well, the only way this can happen, like I said, is for all of the training points to fall outside this region R. Okay, for there to be no xi training example in the region R. Because if there were any point in that region, then the hypothesis would have to be to the left. I think it's probably at most that. Okay, so now we have something we can analyze. So saying that there's no point in R, that's the same as saying that x1 is not in R, and x2 is not in R, and so on. That none of them are in R. Again, all these probabilities are over the choice of the training sample. Yeah?
Assuming that H is always greater than C, because it could also be that H was...
No, that's why I use this algorithm that always picks the leftmost positive. So you can only have one-sided error. That's why I did that, yeah.
So over there, should we ask for no positive xi in R or not?
It's automatically positive because it's to the right of C if it's in R, so it's automatically positive.
Oh, yeah.
Good questions. Okay. So now we can use independence. The data is independent. So we can take this probability of ands and break that up as the probability of each individual xi not being in R. And we just multiply those together. Right? That's just using our independence. And now, what is this probability? What's the probability xi is not in R? Exactly, it's just exactly 1 minus epsilon. Okay, because we chose R to have that size. So this is just 1 minus epsilon to the m. Sorry, I guess I'll continue over here. And now a little inequality that's often useful is that 1 plus x is at most e to the x for all x. So if we use that here, then this is at most e to the minus epsilon m. And we want that to be smaller than delta, right? This is exactly the same as probability error bigger than epsilon is at most delta. So we want this to be at most delta, which it will be if, well, we just have to solve for m to make this true. So what we get is that if m is at least log 1 over delta over epsilon. Okay, so we got our first sample size bound for this really simple algorithm. It sometimes looks, oh, I'm out of time, sorry. But I'm also basically done. Okay, so it looks weird at first that you get these bounds where m has to be at least a certain amount, but it makes sense. You need to have at least that amount of data to guarantee a certain accuracy. But what we've shown is that if we have this much data, at least this much, which is polynomial and 1 over epsilon and 1 over delta, then we'll satisfy this pack criterion. Okay? Maybe I'm out of time, so maybe one question and then.
How would you do the same thing if you allow x to be the whole real line? What distribution would you use?
It's really the same proof works. You don't need uniform distribution. It just makes it easier to think about. You just need to do distance, not an actual distance, but in distribution. You have to move over epsilon distance of the distribution. Yeah, so you can make it work there. It's a little messier. But this is the intuition, and we will do more general stuff, okay? Okay, good. So I guess I'll see you guys this afternoon.